Welcome to the deep dive. Today we're tearing into a single book, but it's one that really contained the blueprint for a whole scientific revolution. We are looking at the 1790 English translation of Antoine Lavoisier's foundational work, Elements of Chemistry.
Yeah, and when the translator, Robert Kerr, brought this to the English-speaking world, he knew immediately. He said Lavoisier had effected a great revolution in the theory of chemistry. That's putting it mildly, honestly.
Right. So our mission today is to unpack how this volume basically dragged chemistry out of, well, alchemy and into the modern age. We'll focus on the new ideas, the logical language, and those really strict quantitative methods he laid out.
And you can feel the urgency just from the translation itself. Kerr mentions he had to rush it, like really rush it, to get it ready for the university session that fall.
Wow, so accuracy over style.
Exactly. He prioritized scrupulous fidelity, getting it right over any elegance of style. He basically knew getting this knowledge out there fast was more important than making it sound pretty.
That really says something about how needed this was.
Oh, absolutely. And think about the practical problems Kerr had to solve just for the translation. He added a whole appendix with rules for converting French weights into English ones, and Lavoisier used Romer's temperature scale, so Kerr had to convert that to Fahrenheit.
So even before you start doing the chemistry, you've got this translation barrier, this standardization problem.
Precisely. It wasn't just new chemistry. It was like learning a new universal scientific grammar just to read the book.
Okay, let's get into that new grammar then, because the language before Lavoisier was, well, you said it, a bit of a mess. Why was the old system so broken?
Well, the old names were just all over the place. Arbitrary, sometimes sentimental, named after the discoverer or where you found the stuff. And worse, many names kept alive ideas about the substance that were just plain wrong, evidently false ideas, as the text puts it.
Right, you can't build a solid science on a language full of errors and old myths.
Exactly. So in 1787, Lavoisier and his colleagues de Morveau, Berthollet, de Fourcroy, they basically had to, burn the old dictionary and start over.
So what was the thinking behind the new names? What was the philosophy?
Utility and clarity. That was the core idea. Name simple substances with simple terms. They often borrowed from Greek and framed the name to express the substance's most general and the most characteristic quality.
Ah, to make it logical.
Yeah, and the text is very clear. This was meant to help beginners remember things by linking the name directly to what the substance is or does.
Makes sense for elements like oxygen, the acid former. But what about compounds? When you start combining things, like to make neutral salts, it gets complex fast. How did the new system handle that?
It forced you to think structurally. For compounds, like these neutral salts, the name had to reflect the three key parts. You had to identify, one, the acidifying principle, it's common to all of them.
Yeah.
Two, the acidifiable principle, the thing that makes this particular acid unique. And three, the basis, whether it's metallic, earthy, or saline.
So the name isn't just a label anymore. It's almost like a mini formula. It tells you how it's built.
Exactly right. It tells you the components. Think about fixed air or fixable air, the old term. It tells you basically nothing useful.
Yeah, very vague.
Lavoisier's system calls it carbonic acid gas. Instantly, you know it's an acid. You know its base is charcoal or carbone. And you know it's been oxygenated. It's a definition baked into the name.
And the sheer number of possibilities must have made this systematic approach essential. You mentioned the scale Lavoisier was dealing with.
Oh, yeah. Get this. They knew of 24 salifiable bases, things that could form salts. That included 3 alkalis, 4 earths, 17 metals.
Okay.
And they had identified 48 different acids, many of which could exist with different amounts of oxygen. So if you do the math, every acid potentially combining with every base. That's 11,152 theoretically possible neutral salts.
Wow. 1,152.
Yeah. Now imagine trying to come up with over 1,000 unique arbitrary names based on who found it or where.
It's completely unworkable. A total mess waiting to happen.
It proves the old way just couldn't scale. The new nomenclature wasn't just helpful, it was the necessary architecture for a growing science.
So this ordered language needed a new kind of physics underneath it, didn't it? Shifting gears from the names to the theory, how did Lavoisier rethink the states of matter? Solid, liquid, gas.
He proposed this elegant dualism. He said every particle in nature is pulled by 2 opposing forces. There's attraction pulling them together, making things solid.
Right.
And then there's repulsion, pushing them apart. And this repulsive force, he argued, is caused by caloric, basically heat.
So the state of matter, solid, liquid, gas, just depends on the balance between these two, attraction versus caloric.
Exactly. It's the equilibrium point. And he was careful, too. He said, we can study caloric's effects mathematically, quantify them, without getting bogged down in whether it's a real substance or just, a principle. He called it the repulsive cause.
That's quite modern, focusing on the effects.
It let him define the term gas generically, an elastic fluid. He saw a gas as just a substance's base that's been, well, dissolved or suspended by enough caloric.
Caloric acts almost like a solvent.
Ah, I see. Like dissolving salt in water, but dissolving a substance's base in heat.
Kind of, yeah. And this led to the universal idea that almost everybody in nature is susceptible of three several states of existence: solid, liquid, aeriform. It just depends on how much caloric is combined with it.
Which then brings in external factors like atmospheric pressure.
Right. The text makes a big point about pressure. Without the atmosphere pressing down, lots of things we consider liquid or even solid would just float off as gas.
They had that great example with ether, didn't they?
Yeah, vivid. It says if the barometer dropped from the usual 28 inches of mercury down to, say, 20 or 24 inches, you just couldn't get liquid ether in the summer.
Too much heat, not enough pressure.
Exactly. You definitely couldn't make it on mountains where the pressure is naturally lower. It shows the atmosphere isn't just air. It's a crucial part of the chemical environment, like a containment vessel.
Ties the theory directly to real-world physics you can measure. Okay, let's move to the proof. The experiments. Starting with air, the famous mercury calcination experiment. What did he actually see happen?
Well, two key things. First, when he heated mercury in a sealed container of air, the volume of air inside went down noticeably reduced to about 5/6 of what it started with.
Okay, so something was removed from the air.
Yes. And second, a red powder formed on the surface of the mercury. The old alchemists called this sort of thing a calc.
Right, so what was this calx in Lavoisier's new system?
That calculus was the mercury chemically combined with the base of the breathable part of the air. Lavoisier realized the mercury was effectively undergoing a slow, gradual combustion. It was fixing or locking down part of the air.
The breathable part.
Right. And by measuring carefully, he showed atmospheric air was made of roughly 27 parts of this breathable air, which he eventually named oxygen, and 73 parts of the leftover, unbreathable stuff, the noxious air or mephitic gas, later called azote.
And the real genius here, the quantitative rigor, was that he didn't just analyze it. He put it back together, didn't he? How standard was that back then, proving your analysis by synthesis?
Oh, it was utterly revolutionary to make it the standard of proof. It's the whole principle of conservation of matter in action. You have to account for everything.
So your work, basically.
Pretty much. They showed you could recreate normal atmospheric air perfectly by mixing exactly 73 parts of that mephitic gas, which they could get from other sources, like dissolving animal matter in nitric acid, with 27 parts of the respirable air they got back by heating the mercury calx.
If the weights and volumes didn't add up, your analysis was flawed.
Precisely. No fudging the numbers.
Then came the other big one, water. An element since antiquity. Lavoisier said no.
Yep, a huge shift. The conclusion was definitive. Water is not simple. The key experiment involved passing water vapor over red-hot iron in a tube.
And what happened?
The iron basically ripped the water apart. It decomposed it.
And the measurements here had to be spot on, I imagine.
Absolutely crucial. Lavoisier found that the oxygen from the water, accounting for 85 parts by weight, combined with the iron, making a black iron oxide, or oxide as he spelled it.
Okay. And the rest?
The other part of the water, the base of what they called inflammable gas, was released. It weighed 15 parts, and it came off as pure hydrogen gas.
So water, 85 parts oxygen, 15 parts hydrogen, by weight. Defined.
Defined by quantitative experiment. Not just an idea, but a measured fact.
This relentless focus on measurement, on quantification, it meant chemistry couldn't be just qualitative descriptions anymore, could it?
No more guesswork. It demanded that chemists verify every result by weighing inputs and outputs. Conservation of matter wasn't just a theory, it was the rule. You had to prove it.
Which also meant needing a common language for weights, didn't it? To compare results across labs, across countries.
Exactly. Lavoisier actually proposed that chemists everywhere should express weights in decimals of their local standard pound. That way, even if the actual unit, the pound, was different in France versus England, The relative proportions between elements in a compound would be universally understood and comparable.
That's a really practical push for standardization.
It was essential for building a global science.
And achieving this kind of precision, especially with heat being so central to his caloric theory, required totally new kinds of instruments, which brings us to the ice apparatus, the calorimeter.
The calorimeter. It was brilliant, really. Simple concept, genius application. They used melting ice because ice, as it melts, absorbs heat caloric at a constant temperature.
Right. Phase change.
Exactly. So all the caloric given off by whatever substance you were testing inside the apparatus went into melting the ice. The amount of ice melted gave you a direct, precise measure of the heat released by the tested body. Double the heat released, double the water collected.
And they used this for some incredibly precise combustion tests, didn't they? Comparing compounds to their parts.
Oh, yeah. The wax example is classic. They burned 1 pound of wax and measured that it melted 133 pounds and 2 ounces of ice.
Okay.
Then, Lavoisier calculated the theoretical heat release. He knew wax was mostly carbon and hydrogen. He burned those separately and summed their heat release, which theoretically should melt 131.76 pounds of ice.
Wow, that's incredibly close.
Stunningly close. It was powerful proof that matter and energy were conserved and that his understanding of the composition of wax was basically correct.
But they were honest about discrepancies too, weren't they? I remember reading about the olive oil test.
Yes, and that's important too. It shows their rigor. 1 pound of olive oil melted 148.88 pounds of ice. But the theoretical sum based on its known carbon and hydrogen was only 138.33 pounds.
Quite a bit off.
It was, and they reported it. It showed that even with this precise method, there were still things to figure out. Maybe the composition of olive oil wasn't perfectly known, or there were other factors. The point wasn't perfect results every time, but a method to rigorously test and refine knowledge.
And dealing with gases required its own specialized and apparently very complex setup, what they call gasometry.
Right. This wasn't stuff you could build in your kitchen. Lavoisier describes these huge, expensive setups. Large water cisterns lined with lead. One held 4 cubic feet of water, had 14 square feet of shelf space inside.
Good grief.
And specialized marble troughs for using mercury to handle gases that dissolved in water. These weren't just tools. They were serious pieces of engineering designed for precise gas measurement and manipulation under controlled pressures. It was a statement that chemistry was becoming a high-precision, high-investment science.
It really is amazing how much of what we take for granted in modern science, the careful measurement, the systematic naming, proving things through synthesis, it all seems to trace back directly to this one work from 1790.
Lavoisier didn't just give chemistry a new theory. He gave it a method, an architecture, and frankly, an ethical standard for evidence.
So if we pull back for the final thought here, what's the ultimate takeaway? Why was this massive, probably painful overhaul so necessary?
I think you have to go back to that number we talked about earlier. The 152 theoretically possible neutral salts from just the known acids and bases at that time.
Right.
Lavoisier's ordered, systematic language wasn't just a nice-to-have, a convenience. It was the only conceivable way to manage the sheer explosion of chemical knowledge that was coming. Without that logical foundation based on composition, the 19th century, with all its discoveries, would have descended into utter chaos.
The language itself enabled future discovery. An incredible legacy. Well, thank you for guiding us through this foundational text.
My pleasure. It's always fascinating to revisit.
And for you, our listener, maybe think about this. Back in 1790, they foresaw over 1,000 possible salts. Today, how many millions, maybe billions of chemical compounds does science deal with? It makes you realize just how vital Lavoisier's legacy of order and quantitative rigor truly is, maybe even more so now than 2 centuries ago. We'll see you next time on The Deep Dive.